check over our homework from last night. The first one, page 452, variable value changing. First question says, many modern rifles use bullets that have less mass and reach higher speeds than bullets for older rifles, resulting in increased accuracy over long distances. The momentum of a bullet is 8.25. What does the momentum become if the speed increases by a factor of 3/2 and the mass decreases by a factor of 3/4? Well, my relevant equation is P is equal to M times V. Let's set my relevant equation equal to my original momentum. This is what I start with. And then let's set that equation equal to my original value, 8.25. This part isn't rocket science, right? This part is just what we have on our data sheet and what's given to us in the question. The next part is when you have to do something. We're going to say my new momentum, Pn, is equal to my new mass times my new velocity. My new mass is going to be 3/2 times m. What's my new velocity going to be in this question? We talked about this a little bit yesterday, right? Because a little bit confusing here. My new velocity will be what? 3/4 v? 1/4. We're reducing it by 3/4. If we reduced it to 3/4, then we'd leave the 3/4 in there. But since we're reducing it by 3/4, we're left with 1/4 of the velocity. Let's factor those numbers out. We get 3/8 m times v, and m times v is equal to 8.25. And I think when you do that math, it works out to be 3.09 kilograms meters per second, which is not the answer that they've given to us here. But we talked about that yesterday as well. Their answer is wrong because they assumed 3/4 as opposed to 1/4, which is correct. Okay. 2. During one part of the liftoff of a model rocket, its momentum increases by a factor of 4. Its mass is halved. The velocity was initially 8.5. What's the velocity now? This time we've got to take a rearranged form of that equation, set that equal to my original velocity, and then set that velocity equal to 8.5. My new velocity will be my new momentum, which is 4 over my new mass, which is half. Oh, this is a little bit tricky, eh? It's 4 divided by a half. It's 8, right? Use your calculator for that, or do you use the grade 7 dividing fractions method? You laugh. You laugh. But I guarantee you, there's people in this room that can't divide fractions. Why? Because you probably haven't done it since grade 7 or grade 8, right? We forget things that we haven't done in a long time. Even if they're not hard, we forget things that we haven't done in a long time. Okay, you can use your calculator, or you can say 4 over half is the same as saying 4 times 2/1. Same thing, right? Multiplied by the reciprocal. That becomes 8/1 times P over M. 8 times 8.5 gives me 68 kilograms meters per second. How many people got both of those questions correct? Oh, you guys are laughing then. The quiz tomorrow is going to be easy, or at least half of the quiz is going to be easy. All right, the other bit of homework you had was worksheet number 1. I want to put up some answers for worksheet number 1 right now. You guys can take a peek at those answers. You're not necessarily looking for solutions here. Some of them I've shown a little bit of work for, some of them I don't. You're not looking for solutions, you're looking for answers. If you got an answer right, then you're probably okay. If you got an answer wrong, then you probably need a little bit of work with it. Okay? Take a look at all the answers, identify the ones you got wrong or the ones you need help with, and then when we're done looking at these, we'll go over whichever ones we need to go over, okay? So just have a look. I'll slowly scroll down so that you can see the rest of them. Let's take a look at question 5, 7, and 8. 5 says a 5 kilogram ball accelerates from rest at 2 meters per second squared for 1.5 seconds. What's the momentum after the acceleration? One of the things that we look at when we see a question in Physics 30 is, what do we got? What do we know about this? But one of the other things that we can sometimes ask ourselves is, how is this the same as something I've already done? Or how is this different than something I've already done? We did a couple of questions in class that are similar to this. Remember a couple of questions where, I can't remember the context of one of them. I think it was a rock falling from the edge of a building. What was the momentum as it struck the ground? The other one was, it was a baseball moving and it fell. What was the momentum of the baseball when it struck the ground? How is that similar to this question, question number 5? How are both of those examples that we did similar to this? Yep. We want to find momentum, yeah, at a specific time after an acceleration has happened, right? How is it different? How is this one different than the questions that we did as examples in class? Dom? Okay, so our givens are different, yeah. So how we find that final velocity will be a little bit different, sure. Both of the ones we did as examples involved vertical motion, right? So the acceleration was 9.81. Here it's quite a bit smaller than that, right? 2.00. Same basic idea, but different givens. So a different equation to find VF and different acceleration. Same basic idea though. Let's say the mass is 5 kilograms. Let's say VI is 0 because it starts at rest. Let's say A is 2.00. We don't know what VF is. That's what we're looking for, right? Our time is 1.50 seconds. Ultimately, we want to find PF, the final momentum. What equation did somebody use to find VF there? The velocity at the end of it all. I know some people yesterday were trying to use VF squared is equal to VI squared plus 2AD. Is that a valid equation for this? Sure it is. All of those acceleration equations are valid. What's the problem, though, if you try to use VF squared? We don't know what VF is, and we don't know what D is. So we get too many unknowns. Like, try it. If it works, great. If it doesn't, because there's too many unknowns, try something else. Here's what I did, or here's what I would have done. I know the acceleration is 2, and I know the time is 1.5, so the change in velocity will be 3. If the initial velocity is 0 and the change is 3, then the final will be 3 as well. So I'm going to say it's 5 kilograms times 3 meters per second, which is 15 kilograms meters per second. How many people got that? Good. Good. 7. A 1 kilogram rock is thrown into the air from ground level at a speed of 8 meters per second. Yep. Okay. Yeah, go ahead. Back to number 5. Go ahead. Oh, okay. I see what you mean. Okay. Okay, I can see that. I can see that. So Mac was bothered a little bit by the fact that on his data sheet it says A average. I didn't even actually realize it said that, but that's not a big deal for us. I'll try to resolve that for you. Okay. It's correct. What we've done is correct, but I can see where the wording of it and the notation of it might have confused you a little bit. When they say acceleration, the average acceleration, so it looks something like that. When they say the average acceleration is delta V over delta T, you can look at that in 2 ways. Look at it and say, like, okay, look, the acceleration of an object is changing a little bit. Maybe you're running a 100-meter sprint and you're accelerating. Let's say it's 50 meters, where you might accelerate the whole time. You accelerate, but your rate of acceleration might change a little bit depending upon, how good your body feels at any given moment in time, or Even if it feels good the whole time, you'll accelerate at a quicker rate initially than you will later on. The gains that you make later on are less than the gains that you make initially. So your acceleration isn't going to be constant the whole way. But you could figure out your average rate of acceleration over that period of time, and you could use that equation to do that. Now, the other thing that it's good for is that if the acceleration is constant, if it's not changing acceleration, we can still use the equation A is equal to delta V over delta T. What we'd really like to see is A average slash constant, because in either case, that's the equation that's valid here. This problem that we have right here involves a constant rate of acceleration. Well, at least we assume that it is. Maybe they meant average, but, or maybe I meant average. I meant constant. But either way, you can treat constant acceleration and average acceleration in the exact same way. Okay, does that make some sense? Okay. Yep. All right, back to number 7 here. A 1 kilogram rock is thrown up into the air from ground at a speed of 8 meters per second. It travels up to a max height, whatever that max height is, and then comes back down to ground level. We want to find the momentum as it strikes the ground. This one bothered a lot of people in both classes, actually. What's going on here? Not what are my numbers. What's going on here? Goes up. What happens as it goes up? As this rock goes up into the air, what happens to it? Describe its motion as it's going up into the air. It slows down. It slows down, it slows down, it slows down, it slows down. And when it reaches the peak height, what happens to it? It stops momentarily, right? Just for an instant in time. And then it turns around and comes back down. And as it comes back down, what happens to it? It accelerates. What's the rate of deceleration as it's going up? Chase? Neg 9.81. Good. What's the rate of acceleration as it comes back down? Negative 9.81. Negative in both cases? Yeah, because as it goes up, it slows down in the positive direction. And as it comes down, it speeds up in the negative direction. So it's neg 9.81 any way you look at it. We can analyze that whole problem going up and down using the same rate of acceleration. Let's do that. Let's say VF squared is equal to VI squared plus 2AD. Ultimately, we want the speed as it strikes the ground, right? So let's get it. The initial speed is 8. Square that. The acceleration for the entire trip up and down is neg 9.81. So put that in. What's the displacement from start to finish here? This one is what bothers people, right? Because we're not told what the max height is. Do we need to find that first? No, we don't. As the rock goes up and then comes back down to where it started, what's its displacement? Final position minus initial position. 0. So let's say 8 squared plus 2 times neg 9.81 times 0, which this ends up being 0. What's the square root of 8 squared? 8. So it's going the same speed as it started. Logically, if you start at 8 and then slow down at 9.81 and then stop, and then speed up at 9.81 for the same distance as you slow down, then you got to be going the same speed, right? So if you can come up with that logically or mathematically like we just did, either way works for us. Now it's an easy question, right? Now that we have the velocity. The momentum is m times v. It's 1 kilogram times negative 8 for the velocity. Gives me negative 8.00 kilograms meters per second. Right? And finally, question number 8 says 1.5 kilogram rock is thrown up into the air, ground level, reaches maximum height of 7 meters, returns to the ground. Almost the same thing, right? Except our givens. It's slowing down, speeding up, but we don't know what the initial velocity is this time. This time we know what the max height is. Here's what I want to do for this. Analyze only the trip down. Listen, if you want to try doing what you did right here, go ahead and try. There's nothing wrong with that. It's the same situation with different givens. If you want to try VF squared is equal to VI squared plus 2AD for the entire trip, up and down, that's fine. But you're not going to have enough givens to get an answer. You're going to have too many unknowns. So try something else. Let's try analyzing the trip down. When I do that, I would say that VI would be 0. Because the trip down, it starts at rest, right? Plus 2 times neg 9.81. And if we're analyzing the entire trip, D is 0. But analyzing only the trip down, D would be negative 7 meters. So solve for VF there. Okay, whatever that works out to be. Square root of 2 times 9.81 times 7. And then multiply that by M to get the final momentum. Is that okay?